My name is Stephen Rothman, and today I'm going to give a brief outline about solving basic 2x2 game theory models. This introduction is for my Global Issues and Policies class. It is not intended as any kind of substitute for a full game theory class or any major game theory class, because we're only going to discuss 2x2 models, and it's only going to be most basic set of information to help students learn to solve those problems. Before we begin discussing 2x2 models, it's important to review just a little bit about game theory. Game theory provides us a set of tools for modeling interactions between individuals or between other actors, states, in your own life or in any kind of field, actually. And just like any set of tools, they could be misused or misunderstood or broken, misapplied, and we can get the wrong outcomes. We can manipulate it to our advantage. We can do all kinds of things that don't necessarily reflect good science or good use of the tool, good use of game theory. So it's important to keep that in mind. What does game theory do? Well, it allows us to formally model interactions between several actors. What does that mean? Formally model something means to create a mathematical model. Now, even though we're not going to be doing much math in this section, anything that we do can be put into mathematical formula or mathematical equations. The ones we will be working on are quite simple and don't require a great deal of math. We can do pretty much everything in our head. But in some cases, if we had expanded models, it would be more useful to do them in equation form rather than in kind of graphical form, which is how we will do it for this class. And the purpose is basically to find an outcome or predict how interactions lead to a particular outcome. There's a few assumptions that we need to think about before we begin. First of all the players are formally rational. When I say formally rational, I mean they are strictly rational. If you're not familiar with what that means, it's better to find the information elsewhere. I'm not going to go over that right now. In addition, all the players share common knowledge about the game. This means that all the players know what the rules are. They know the values of the outcomes for each of the other players, and they know that all the other players know the rules and the outcomes of the game. So basically, all knowledge is known. Everything is out on the table. It's not like playing poker, where you're hiding your cards from your opponent. Everything has to be out on the table. This is a basic diagram of what a 2x2 game will look like. We start with just two players. So in this model, we can see each player has two choices. Player 1 has choice A or B, and player 2 has a choice C or D. There's no indication here what these choices mean or what the values of the outcomes are. All we can see here is that there are two choices for each player and that any combination is possible. So AC is possible, AD, BC, or BD. All four of those things are possible. And that does create four outcomes. So there are four combinations when there are two players with two choices each. In this case, the order doesn't matter. Both players are making the choices at the same time. So for that reason, there are only four outcomes. And we can write these four outcomes like this, and we just put those four boxes on the left side here. So we have four outcomes: AC, BC, AD, and BD. And from each outcome, the players will have some value. So if player 1 chooses A and player 2 chooses C, that will give some value to that outcome AC. Player 1 will value it either a lot, somewhere in the middle, or not very much. And they value the outcomes, not the choices. This is very, very important. The outcomes are important. The choices don't have inherent value amongst themselves. Okay, we don't place moral value or otherwise value on a particular choice. We place the value on the outcome, the combination of choices between the two players. So we can put those values back into the 2x2 model, and you can see that we have EV1, for example, in the top left corner, is the expected value of that outcome for player 1. So when player 1 chooses A and player 2 chooses C, we get the top left outcome. So that has some value to player 1. And we can actually put numbers in these cases later, which I'll illustrate. So I can put numbers in those outcomes just as I've done here, and you can see that when player 1 chooses A and player 2 chooses C, player 1 values that outcome at 4. Now that 4 doesn't necessarily represent an absolute value. It doesn't mean it's worth $4 or $4 million. It could be worth anything. But the 4 is a relative value. So 4 is more valuable than 3. 3 is more valuable than 2. So given that information, if I ask you what is the least valuable outcome for player 1, the answer should be pretty obvious. Hopefully you've said the outcome BD, where player 1 chooses B and player 2 chooses D. The value for player 1 is 1, and that is the lowest value available. If I asked you what is the second most preferred outcome for player 2, which of the outcomes would you say is the second most preferred outcome for player 2? Which is the second most preferred outcome for player 2? Well, hopefully in that case you just looked at the red numbers, and we have 4 red numbers, 4, 3, 2, 1. And I know 4 is the most preferred outcome, and 3 is the second most preferred outcome. So which one is that? Well, that's the combination of choices, or the outcome BC, where player 1 chooses B and player 2 chooses C. You can see the red number there, 3. That's the second most preferred outcome for player 2. And we can model a real life situation. We can put in real countries and real choices, and I can go figure out what the values of those outcomes are, or the relative values, which one is most preferred by the United States, which one is most preferred by Japan. And then I can put all those numbers in there, and I can actually create a situation like this one, where we have the United States and Japan that are discussing their trade relationship. And we can say that they have 2 choices. They can have free trade with the other country, or they can raise taxes. So the United States can have free trade and Japan can raise taxes. That would be the top right. We could have both choosing free trade, the top left, both choosing tariffs, the bottom right, or the United States choosing tariffs and Japan choosing free trade, which would be the bottom left outcome. Now, I didn't put the values of the outcomes in here. We would have to get those from research. We'd do our research and we'd figure out which of those 4 outcomes does the United States prefer the most. Just by our understanding of general U.S. policies, we might predict that the top left would be the most valuable for the United States, a country that has been pursuing free trade with Japan for a very long time. So we might give that a 4. Japan, on the other hand, might not see that outcome as their most preferred. They might see something different. But we'd have to, again, do research to discover that information. Now that you're familiar with what a 2x2 game looks like, I want to talk a little bit about Nash Equilibrium. Nash Equilibrium is basically how we solve these games, these 2x2 models. It was developed by, you might guess it, a man named Nash, or actually John Nash, at Princeton University during his PhD. He has received the Nobel Prize in Economics, as well as a lot of other awards for his work developing game theory and developing the concept of Nash Equilibrium. So he's a very, very important, famous person today who's basically, his theories are now involved in every single science out there. There is actually a famous movie about him. It's called A Beautiful Mind. It's not about his game theory so much as about his personal life and his struggles. It's a very good movie. There's only one small bit of game theory in there, and it doesn't get it perfectly correct, but it is a good movie nonetheless if you're interested. What did he create? Well, he created a theory of non-cooperative interactions. He was developing a theory that suggested Adam Smith was wrong. And Adam Smith, you might know, is the founder of modern capitalist economic theory. And his theory suggested that when we pursue individually preferred behavior, if everybody does what their most preferred choice, if everyone chooses based on their most preferred choice, personal preference, then we will get to optimal outcomes. We'll get to a free trade system, a market economics. What John Nash showed is that sometimes it doesn't occur like that. And he showed that even when people pursue their own interests, sometimes we get to outcomes that they don't actually prefer. And they would prefer a different outcome, but they can't actually get there. And we'll illustrate that in a little bit with the Prisoner's Dilemma game. So what is Nash Equilibrium? Well, Nash Equilibrium is a set of choices or a particular outcome where neither player wants to change their decision. It's stable. Nobody wants to play anymore. They're done. They've made their choice and they're sticking to it. They don't want to change their choice. Now, as I mentioned, that outcome is not always the best outcome. It may not be preferred by either player. It may not be preferred as a social optimum either. The important concept is that it's stable. It's also what we would consider the predicted outcome. It's where we would predict will happen in a set of circumstances. Now, when we want to solve one of these 2x2 games, we can take all of the information we've had, 2 players, 2 choices, and their values over the outcomes, each player's values over the outcomes, and we can solve to define this stable position. Now, when we do this, it's actually quite simple, doing it graphically. First thing we should do is cover up one of the sets of choices and only concentrate on the outcomes of one player, the values over the outcomes. So in this case, I've covered up choice D. And I've said, okay, let's imagine player 2 chooses C. In that case, what will player 1 do? Well, they have a choice between A or B, and I've covered up the values of the outcomes for player 2, so only you see the values for player 1. Now, in this case, we see the value of player 1 choosing A is 4, and the value of choosing B is 2. 4 is greater than 2, so player 1 is going to choose choice A if player 2 chooses C. Hopefully that is clear. And we can do the same thing by covering up choice C and look at choice D only. Let's imagine player 2 chooses D. That's what they choose. In that case, what is player 1 going to do? Will they choose A or will they choose B? What do you think? Well, hopefully it's quite obvious that 3 is greater than 1. 3 is more preferred than 1. So player 1 prefers choice A over choice B here. They prefer the outcome AD over the outcome BD. So we can highlight that. When you're doing it on paper, you can use a little star or something to make a note that that is the preferred outcome for player 1 given player 2's choice. Now we have an interesting thing here. We've noticed that player 1 will always choose A no matter what player 2 does. If player 2 chooses C, player 1 wants A. If player 2 chooses D, guess what? Player 1 still wants A. This is called the dominant choice. Player 1 will always choose A over B. Now remember, this is only an artifact of the game that I've drawn. Because I put the numbers in as I did, I created the numbers. I've created the situation where A is dominant over B. This is just a model. It represents something in the real world. I haven't told you what it represents, so it's sort of meaningless. It's just numbers. I'm just explaining how to solve this for Nash Equilibrium. Okay, there's no application here because there's no story. Where those numbers came from, who these players are, what their choices are, we don't know. And of course, now I know, though, that player 1 is going to choose A, and so I can look at player 2's choices and say, okay, if player 1 chooses A, what is player 2 going to choose? They will choose C, because C has a value, expected value, or the outcome AC has an expected value of 4. The outcome AD has an expected value of 2 for player 2, and they prefer 4 over 2, so they're going to choose C. Now, because of this, I know what the outcome will be. Player 1 is always going to choose A, and therefore player 2 is going to choose C, and that's going to be the outcome. That is a stable outcome. It's Nash equilibrium. We could do the same just to verify. If we say, let's imagine player 1 chooses B, which of these two will player 2 choose? But we can see that 3 is greater than 1. 3 is the outcome value for player 2 of BC. 1 is the outcome value of player 2 of BD. So 3 is greater than 1. So we know that player 2 will always choose C. Player 2 will always choose C. Player 1 will always choose A. And therefore we know that Nash equilibrium is going to be the outcome AC. Now this doesn't, as I mentioned, it doesn't have to be this way. Just because of the numbers that I put in there, it makes this game actually relatively simple. There are a lot more interesting games. Okay, and one of the most interesting games that we have available to us is called the Prisoner's Dilemma model. This is based on a very famous story and actually is widely used by police officers to interrogate prisoners. So let's imagine 2 people are accused of a crime and the police arrest them. And when they arrest them, they separate them. They put them in separate jail cells or separate interrogation rooms. And the police tell each person separately the same story. Okay? They tell them, if you cooperate with us and tell us that your partner was in charge, he or she was the one who created the criminal activity, we will give you a deal and you will go free. However, if your partner tells on you and you don't say anything, you're silent, you'll go to jail for probably about 10 years because someone is going to testify against you. Your friend in the other cell is going to go to court and say it's all your fault, and so you're going to go to prison. Now, if you both tell on each other, you'll both go to prison because you're both being cooperative. Will reduce the sentence a little bit. You won't get 10 years. You're going to get 5 years. Okay. Now, the last part, they probably don't mention to the prisoners in real life, but in the game, because we have common knowledge, we have to tell the prisoners in our system, if you both remain silent, you will go to jail for probably 3 years. Now, what's the problem here? Well, if they both stay silent, they will go to jail for 3 years because they have some evidence, but not a lot. But if one person talks and one person says that the other person is guilty, they will go free. So what do you think will happen? Do you think they will both stay silent? Do you think one person will stay silent and the other person will talk to the police? Or do you think they will both end up talking to the police? What's your guess? Have you figured it out? Well, let's take a look. Now, if we try to model the same game that we just had, imagine the 2 prisoners. I can put player 1 and player 2 for prisoner 1, prisoner 2. And they have 2 choices. They can stay silent or they can snitch on their partner. They can turn their partner in to the police. Okay. And we can put some numbers based on the information that we've had before into these boxes based on preferred outcomes. So for player 1, if they snitch on their partner and their partner stays silent, that's the bottom left corner, then the player 1 goes home. They're free. And player 2 goes to prison for 10 years. So player 1 is very happy with this. They get to go home. That's the most preferred outcome, so that gets a 4. On the other hand, player 2 goes to prison for 10 years. That's the most they can go to prison for, so that's the least preferred outcome, so that gets a 1. And the opposite, the reverse, is actually true in the top right. Player 2 snitches on their partner, player 1 stays silent, player 2 goes home, and they prefer that the most, so that's a 4. And player 1's least preferred outcome, because they go to prison for 10 years, so that gets a 1. Okay, and we can fill in the bottom right box. Now, if both snitch on their partners, they both go to prison for 3 years. I'm sorry, they both go into prison for 5 years. So that's not good, but it's not the worst outcome. 10 years is the worst, 5 years is less worse, the second worst outcome. And on the top left, if they both stay silent, they only go to prison for 3 years. So that's a little bit better. So we have basically the outcome, most preferred outcome 4, going home free. The second best outcome, that's represented by 3, means you go to prison for 3 years. The next most preferred outcome, represented by 2, means that you go to prison for 5 years. And the least preferred outcome, represented by 1, means you would go to prison for 10 years. And we could actually put the numbers of prison years in there instead of those 4, 3, 2, 1, but generally, for basic applications, we use preferences rather than the value of the outcome. So, when we try to solve the Prisoner's Dilemma game, we can start by doing the same process we used to solve the previous game. We eliminate one of the choices, and in this case, I've said, let's imagine player 1 stays silent. So I've eliminated the choice snitching on the partner. And I say, well, what will player 2 do? Well, here we have a choice again of staying silent or of snitching on the partner. The red numbers represent the expected value for player 2. So, what will player 2 do when player 1 stays silent? Will player 2 stay silent, or will player 2 snitch on their partner? What do you think? Well, in this case, I hope, again, the answer is quite simple and obvious, because the numbers represent preferences. 4 is more preferred than 3, so player 2 will snitch on their partner. And this makes a lot of sense, because when player 2 snitches on their partner and player 1 stays silent, player 2 goes home free. So that is the most preferred outcome. And we can designate that outcome with a little star. And using the star is very helpful when I'm solving these games on paper. And I can do the same thing again. When player 1 chooses snitch on partner, what will player 2 do? Will player 2 stay silent, or will they snitch on their partner? Again, we're comparing the red numbers. So what do you think? Well, hopefully you've thought quite simply that 2 is preferred more than 1, and so the player 2 will snitch on their partner when player 1 snitches on their partner. And again, this makes sense. Why? Because if player 2 stays silent, they will go to prison for 10 years. If they snitch on their partner, then they will go to their prison for only 5 years, and that's much better outcome for them. So we can designate again that position with a star. Now what we have here is again a dominant strategy or a dominant choice. Player 2 will always snitch on their partner. This is interesting. This game is symmetrical. It's the same for player 2 and player 1. Now we can solve the game the same way we did for player 2 for player 1, but we will get the same result. Player 1 is always going to snitch on their partner. And I'll let you solve it on your own on paper if you'd like to go through the steps. But what does this mean? When we put it all together, we find that there's only one place with 2 stars. Now, any place you find in the game that has 2 stars, like the bottom right, is going to be considered Nash equilibrium. It is a stable solution. Now, we're looking at this, and it seems quite odd. Both players are going to snitch on their partners. They're going to prison for 5 years. Both of them would prefer if the other person was silent, but you cannot control the other person's action. You can only control your own. And if they could actually move themselves both up into the top left corner, they'd both be better off, but it's very hard because once you're in that top left corner, there's a very strong incentive for someone to snitch. When both people are quiet, if one person snitches, they go home free. Okay, so there's a very strong incentive. So you always end up coming back to the bottom right. So this is considered Nash equilibrium. It's stable. Nobody wants to change their position by themselves. If you change, you'll be worse off. The problem with this game and why this game is so interesting is because the top left is the optimal solution, the social optimum. That's better for both people, for both players of the game. But it's very, very hard to stay there. Again, if you go there, if you try to move from the bottom right to the top left, you end up in a situation where both players want to change their choice. If they're both staying silent, they're going to go to prison for 3 years. If either person decides to snitch, they go home for free. So they're going to switch. And when they both switch, you end up back on the bottom right corner. That's why it's a Nash equilibrium. Now, hopefully, you've been able to understand the basics of solving Nash equilibrium in a 2x2 game. There's one thing I want to caution you about. That is that not all games have a Nash equilibrium that you can solve like this. This is called a pure strategy Nash equilibrium, and sometimes the pure strategy Nash equilibrium does not exist, in which case you will have no squares with 2 stars. And sometimes you may have more than one square with 2 stars, and you may have 2 or 3 or 4 Nash equilibria, depending on how you draw the numbers. So be aware of this when you're moving forward solving your games on your own. You may not have any Nash equilibria in this form. You may not have any pure strategy Nash equilibria. And you may have more than one. We will also discuss later, perhaps, the idea of mixed strategy Nash equilibria, which will help you learn how to play a game called rock, paper, scissors, or in the West often referred to as matching pennies.